Good morning. My name is Igor Peltashov, and in the next 20 minutes or so, I am going to talk about structural heterogeneity, how it complicates mass spec measurements at the intact mass level, and what can be done about it. So intact mass measurements, of course, have become a very popular way to deal with biopharmaceutical characterization in the past several years. And in my presentation, I'm going to focus mostly on intact mass measurements done under native conditions. It provides all the benefits of measurements that can be done under natural conditions, but in addition, you can look at quaternary structure of your proteins, the interactions with physiological partners, as well as therapeutic targets. So when we talk about heterogeneity, of course, we realize that production of proteins is a high fidelity process because essentially it's typing of a genetic template. But unfortunately, most of the proteins that are of interest to biopharma are glycoproteins. And of course, glycosylation introduces a considerable degree of structural heterogeneity. And we're going to look at some extreme examples today. On top of that, very frequently we have to deal with man-made heterogeneity. So typically these designer PTMs are using some type of chemical conjugation, be it synthetic polymer, a drug, or maybe in the case of synthetic vaccines, it's a conjugation of antigens, multiple antigens to recombinantly produced carrier protein. In all of these cases, we have to deal with a very significant extent of heterogeneity. And on top of that, of course, now we have to deal with gene therapy products, with non-biological complex drugs, which include nanoparticles, liposomes, and so forth, and related products that are produced enzymatically. So there is no genetic template whatsoever, such as heparins. And so all of these products are extremely heterogeneous, and the analysis becomes very challenging as far as mass spectrometry is concerned. So in my talk, I will mention briefly the classical method of dealing with this problem, native LCMS, and then I will switch gears and talk about two techniques developed in our lab, limited charge reduction and cross-path reactive chromatography. So first thing first, native LCMS and why it is inadequate in some cases. So first of all, it's a wonderful technique. So native LCMS, either size exclusion or ion exchange chromatography when combined with online mass spec detection, it really allows many biopharmaceutical products to be examined in great detail. And so I have an example here taken from our old work that was published a few years ago. So I'm not going to go into much detail. Suffice it to say that when you look at relatively small protein therapeutics, in this case, this is interferon beta-1a, you can use chromatographic dimension to separate various isoforms based on their glycosylation status, based on presence of deamidation and so forth, and then use mass spec as a means of identifying all these PTMs. Now, this rosy picture changes considerably when we look at more structurally heterogeneous products. And so here we add pegylation on top of glycosylation and deamidation. And so even though we do see various chromatographically resolved species, when we look at mass spectra of the corresponding isoforms, they're all shown here in the inset. So they all look alike. And just by looking at MS1 data alone, you really, in this case, cannot make any conclusion as to what you're actually dealing with. So that is the challenge. And of course, addressing this challenge requires different tools. So we need to start thinking outside of the box. Pegylation, of course, introduces an extreme degree of heterogeneity in all biopharmaceutical products. And the reason for that is polydispersity of synthetic polymers. But you don't have to deal with pegylated products in order to experience these difficulties that are associated with heterogeneity. So glycosylation is an example that I alluded to a few minutes ago. So, and let me illustrate it by using maps produced using two different types of architecture. Typically, we deal with maps that have IgG architecture. And here you deal with a relatively modest level of glycosylation, just 2 sugars per molecule. And that's fairly manageable. We do have heterogeneity, but we can address that easily using just mass spec alone. So we can clearly see a glycosylated species. We can see various degree of glycosylation. All these measurements, all these conclusions can be made based on just mass measurement alone. Now let's switch from familiar IgG to another map, and this time we're going to use IgE architecture. And of course here we have, instead of just 2 sugars, we have 14 sugars. And so the level of heterogeneity that is associated with this extreme glycosylation is very considerable. And so now we can no longer distinguish among various glycoforms. So the spectrum is shown here at the bottom left side of this slide. So peaks are very broad, and in fact, even a simple task of assigning charges can become very complicated. So very frequently we assign the charges by simply assuming a certain mass, because we already know from bottom-up measurements, we know the sequence, we know the extent of glycosylation and so forth, and then we can put these numbers here. But when you deal with a totally unknown molecule, this task becomes very complicated, and frequently it requires different tools. So what we're using in this case is limited charge reduction. So the technique is, the idea of the technique is very simple. So you select a very narrow population of ions from a convoluted mass spectrum, and then you subject these polycations to reactions with either electrons or anions. So that reduces the charge of your polycation, and you generate a ladder of charges, as shown here. So again, this is this mass spectrum, full-scale mass spectrum of IgE. So clearly we see multiple features here. Some of them are better resolved, some of them are not so well resolved. And here is an example of how we can address this heterogeneity. So we select a narrow population of ions here, and then the limited charge reduction produces this very nice ladder from which we can calculate both charges and the mass of our precursor ion. And so not surprisingly, it corresponds to the intake molecule. However, if we move the precursor selection window to low MOVZ range, now we have a different ladder. And so that corresponds only to a half a molecule of IgE. And we can actually see even smaller fragment if we move the MOVZ selection window further to the left. So that would be just a single heavy chain. So in this case, again, we had some prior knowledge of what the mass should be. Our predictions, they actually were consistent with the results of the limited charge reduction measurements. In some cases, we don't have such knowledge, and I want to show an example here. So this is actually a synthetic vaccine produced by conjugation of nicotine to a diphtheria toxin, which was produced recombinantly. So diphtheria toxin in this case, it lacks glycans, so the mass spectrum is just beautiful. It's shown as a black trace here. However, when we look at two different fractions of the final product, one is more conformationally stable, shown with the blue trace, and another one is less conformationally stable, shown with the red trace. Here the peaks are very broad, and even if you deal with the trace shown in the middle, kind of the commonly used ways to deconvolute this mass spectrum begin to fail. So this is what MaxEnt, this is a vendor provided deconvolution software generates in this case. Of course, this is nonsense. We have a bunch of peaks that have little to do with the reality. If we use a different tool, UniDeck, we actually have one major peak, and as you will see later, the number produced by UniDeck for this peak actually makes sense. However, we do have a collection of other peaks which turns out they're just artifacts. So now, in contrast, let's take a look at how we can measure the mass of these two products using limited charge reduction. And so initially, we're going to focus on the most stable fraction of the vaccine component. So here, a limited charge reduction produces very nice ladders. And so from this graph, we can estimate that the most abundant mass is close to 63.2 kilodalton. So it turns out that UniDeck overestimated this mass only by 100 daltons. So this is actually pretty good. But what UniDeck could not process absolutely is this less stable component of the vaccine. And so here we deal with a convoluted spectrum. Again, by looking at it, we cannot really say what this part of the signal represents. Could this be partially unfolded protein species? Could it be low molecular weight impurities? We don't know. But limited charge reduction solves this enigma in a very elegant way, so we can obtain masses for all of these ions. Turns out both masses are slightly higher than what we measured for the most stable component of the vaccine. And this mass that represents the ions at the low MOZ region of the spectrum is even higher. And so from that, we can not only determine the extent of haptenation, but we can actually clearly see the correlation between the extent of conjugation and conformational instability of the carrier protein. So this is perhaps is not a surprise to a biophysicist that more extensive conjugation leads to loss of conformational integrity. But as far as experiment is concerned, this information can be only produced uniquely by limited charge reduction measurements. Now, let me show you an example of actually taking advantage of the fact that measurements can be done under native conditions. And I also want to use this opportunity to illustrate some limitations of the technique and how we can overcome them. So the spectrum that you see here represents a complex of haptoglobin and hemoglobin. So haptoglobin, of course, is a hemoglobin scavenger, and it's a very heterogeneous protein in a sense that not only is it extensively glycosylated, but it also has multiple isoforms where the quaternion structure is different. So hemoglobin dimers bind to the heavy chains. So heavy chains are shown as red spheres here, and heavy chains of haptoglobin are connected to each other via light chains, which are shown with blue ovals here. So the spectrum is very convoluted, so we can clearly see the presence of unbound hemoglobin here, but then the rest of the spectrum is very difficult to interpret. Again, limited charge reduction gives us a unique way to find out what these masses are, right? So we can clearly see two different isoforms complexed with hemoglobin dimers. And unfortunately, after that, we stop. because the rest of the spectrum lies above MOVZ 8000, and as it turns out, 8000 is the hardware limit for our instruments. So we used a quadrupole time of flight in this particular instance. So our quadrupole cannot mass select ions above MOVZ 8000. And of course, this is a very common problem. So what we can do in this case, so one of the ways to address this problem is to do something very counterintuitive. So we actually use supercharging in solution in order to move the entire spectrum to the left-hand side, right, to increase the charges. So we are doing that using NBA, nitrobenzyl alcohol. So this is a very common supercharging agent. And when we apply that, so pretty much the entire spectrum moves outside of this purple window. So purple window is, we cannot make mass selection there. And so now we can repeat our measurements. Of course, the first two parts of this distribution, we already dealt with them. But now we can also do it with this other part of the distribution, which has not been accessible to us previously. And now we can see larger haploglobin isoforms complexed with hemoglobin. So this is really an interesting case when you do one thing in solution and totally opposite thing in the gas phase. And as a result, you actually obtain meaningful data. So now, since we started talking about haptoglobin, and to our group, it has been an epitome of heterogeneity for a very long time, I wanted to address another issue. So the structures that I have shown to you before, so these are part of so-called phenotype 2-1, but there is another phenotype which is much more homogeneous because it contains only a single quaternary structure, as shown here in this slide. Actually, this should be 1-1. I made a mistake. Now, if you compare the spectra of these two phenotypes, of course, the larger species are absent from haptoglobin 1-1. But when you look at the region of the spectrum between 5 and 6,000, it looks like there is almost perfect overlap. And you would be tempted to say that these are the same molecules, right? Same masses. It is interesting that when you do limited charge reduction, it actually tells you a different story. So the charge states for these peaks in this part of the distribution are different. So just by chance, they overlap almost perfectly, but the masses are different. And so these are the distributions of masses that we get from limited charge reduction measurements. So if that's true, it probably reflects difference in the glycosylation patterns. Right, but how can we prove that indeed we're dealing with different glycosylation patterns? Well, the easiest way would be to deal with that problem would be to break the sulfide bonds and look at the heavy chains of the haptoglobin. So these light chains are not glycosylated. Each heavy chain contains 4 glycans. So for these particular species, there would be 8 glycans in total. Unfortunately, haptoglobin becomes extremely unstable when you break disulfides and heavy chains precipitate. So it's a very challenging measurement. And so here is my opportunity to introduce and highlight another technique that we recently developed in the lab, cross-path reactive chromatography. So the way it works, we actually do chemical transformations inside the chromatographic column. And then we look at the products online using mass spec as they emerge from the column. So here's my 2-dimensional representation of the chromatographic space. So horizontal axis is time, vertical axis is position. inside the column, and at time 0, we introduce reagent plug. So in this particular case, it would be a plug of reducing agents such as TCEP or DTT. And then with some delay, we introduce the protein. Of course, the chemical reagent is a very small molecule, so it travels a total permeation limit. And at some point, protein will catch up with the reagent, and the trajectories would intersect. And so that's where your limited charge disulfide reduction would begin to occur in this particular case. And then you would have products. Products would emerge from the reagent plug, and they would continue going through the column, and they would elute at 2 different time points, right? And so here, that would give you, that would be done very quickly. So you, within just a minute or 2, and that would give you an opportunity to look at these metastable species and determine their glycosylation patterns. And so when we look at, when we do this experiment with haptoglobin 1,1, so this is the mass spectrum of the heavy chain alone, which we were not able to obtain using any other means. And so you can easily interpret the glycosylation patterns here. So notice that the glycans are very mature, fully sialylated. And this is very different from what we have in the case of haptoglobin 2,1. So again, it's only heavy chain, but we have much less mature glycans, and so glycosylation pattern is very different. So now going back to limited charge reduction measurements, so these are the 2 distributions that were obtained by limited charge reduction. And so now we can compare them with the results of XPRC measurements simply by doing the convolution. Remember, XPRC measured glycosylation pattern for a single heavy chain. Now we want to do convolution to see what the predicted mass profile would be for the intake molecule. And so that's, these are the results in red and brown shown for a convolution of the XPRC results. So this is a very nice agreement, and so obviously it was not a surprise to us because we know that LCR is a very powerful technique, but it's nice to see that we have such a remarkable degree of agreement between 2 very orthogonal techniques. So my time is running out, and so I'm not going to read my conclusions from this slide. Just want to say that these 2 techniques, limited charge reduction and cross-path reactive chromatography, are really powerful techniques that I hope are going to see more and more use in biopharma in near future. And unfortunately, because of the time limitation, I couldn't talk about a variety of other very powerful ways to deal with structural heterogeneity. But I hope you would be able to look at that in the book that is coming up in October. So it will be published in just 2.5 months. So that has much more comprehensive information there. Finally, I want to show the most important slide. So these are the wonderful people who actually did all this work that I showed in today's presentation. And I also want to acknowledge financial support from the National Institutes of Health and from our industrial partners, Biogen and Pfizer in particular. And thank you very much for your attention.